In this lecture, we want to look at red-black trees. Red-black trees, like AVL trees, are balanced. That means that the height of the tree grows at the rate big O of log n as new insertions occur. Red-black trees are an alternative to AVL trees. They have a somewhat looser balanced condition, and this means they require less overhead. They also require less memory than AVL trees. Recall from our AVL trees that we have to keep track of the height of the left and right subtrees. This is a red-black tree, but it will illustrate the point I want to make. Assuming that we inserted a 5 here last, then you have to backtrack and check the height of every subtree, which means you have to check the 10, the 30, the 50, but to calculate the height of the right subtree of 50 means going this way. In other words, you have to examine the entire tree. Therefore, to avoid this situation, you need to store the height information and keep it up to date. By that I mean that each node in the tree has not only data, left child and right child, but also left height, right height. This means a 5x increase in storage. That is, if you have 1,000 data elements, you'd have to have 5,000 cells of memory of the size that references require for that platform to store the data. So we have a 5x increase in storage requirements with AVL trees. With red-black trees, this is not the case, therefore it's more efficient. Also, you have to consider the cost of calculating the heights of the subtrees along the insertion path. Because the path is guaranteed to be in big O of log n, that is the height of the tree, that path can't be worse than log n, then you still maintain big O of n behavior. However, there's more overhead associated with it, which means longer empirical times. So we have a 5x increase in memory required for AVL trees, plus the overhead of maintaining the heights. And so they're not really desirable. Red-black trees are an alternative that are more efficient. So for these reasons, red-black trees are the structure of choice if you need a balanced tree. And there are applications for dictionaries or maps where you really need to have the data in order. And in these cases, red-black tree is the structure of choice. So now let's discuss the structural and ordering properties. Remember that the property of the AVL tree was the difference between the left and right subtrees cannot differ by more than 1. However, that restriction does not apply to red-black trees. Very often students think that the definition of a balanced tree is the AVL condition. But that's not the case. The definition of a balanced tree means that the height increases at the rate log n as new nodes are inserted. But it's very much the case that the difference in height between left and right subtrees can differ by more than 1 if we're not talking about AVL trees. So that holds to be the case here. So I want to switch to the sketch pad and talk about a simple idea that underlies this first. Each node in the tree is colored red and black, and the root node is always black. So we will give this a B. Notice what we can have here. The properties of these trees require the same number of black nodes down every path. Okay, so here, from the path from root to leaf, we have 3 nodes, 3 blacks. And on this side, from root to leaf, we have 3 blacks. Therefore, this tree is valid. This tree is valid. You probably would not end up with a tree like this by doing an insertion, but it's a valid tree. The point here is that there are 3 black nodes on this side and 3 black nodes on this side. We also have red nodes, which are interspersed here and here. What this means then is one side can be twice as long as the other side. But part of this, the requirements are that you cannot have two reds in a row. And so this means you can have red, black, red, black, red, black, or black, black, black. So one side can be twice as long as the other, but it's still going to be in big O of log n. So let's take a look at these structural and ordering properties. Every node gets colored either red or black. Now there's nothing special about the colors red and black. It could be a black and white tree. It could be a green and purple tree. However, the convention is red-black. The point is there are two colors for the tree. So each node gets a color, either red or black. The root node must be black. It always is black and cannot change colors. New insertions other than at the root are always colored red. Then every path from root to leaf must contain the same number of black nodes. Finally, no path may have two reds in a row. You can have an unlimited number of blacks in a row, but you cannot have more than one red in a row. Two in a row is not allowed. And then null references, that is, if there isn't a node there, then it's considered black. So you can see here the root node is black. And every path from root to leaf contains the same number of black nodes. So imagine that we have a subtree here. We can only have one black node in order to maintain this property. So we have 3 here, 1, 2, 3 here, down this path. And finally, down this path, we have 3 blacks. So these are the rules that govern the structure and order of a red-black tree. When you do a new insertion, it's colored red. Thus, I think you can see that as you insert new nodes, you're going to have 2 reds in a row. When you inserted a leaf node that was red, you insert a new node and it is red, you have 2 reds in a row, and you will have to deal with this problem in some fashion. Therefore, what always motivates any kind of change to the red-black tree, or fix-up step as we might call it, is a red violation. Red violations occur when a newly inserted leaf node lands on an old leaf node that was red. So here's an example of a red-black tree. As you can see, the nodes are colored, and the black nodes are actually gray so that they will be visible. But they're the same number of black nodes down each path from root to leaf. So there are 3 leaf nodes, there are 3 paths from root to leaf. This path down the left-hand side has the 50 and the 10. This path has the 50 and the 90. And this path has the 50 and the 90. Notice that this tree does not satisfy the AVL tree conditions, but it satisfies the red-black tree conditions. If we inserted the 5 here, then backtracking we can see that the 30 node is out of balance and would have to be rotated to bring the tree back into the AVL tree condition. However, that's not the case for this red-black tree. Thus, red-black trees have a somewhat looser condition, and this means less overhead. So when you insert a new node, it may cause a violation because of having 2 reds in a row. In this case, you have to adjust the tree in some way to bring it back into conformity. So there are 2 adjustments that can be made. A color flip, in the case of a red ant, rotation, either a single or double in the case of a black ant. So let me show you the 2 conditions that we're talking about. Let me color this black, red, red. These are the 2 conditions that we're going to examine here. The first one is a red ant, or a black ant condition rather. This is the black ant. Assuming we had the 8 and the 10 here in this tree, and now I insert a 5. New insertions are always red. I have 2 reds in a row. This is a red violation. Now I want to label these. This is the child node, and this is the node that caused the problem. This is the parent, the 8, and the 10 is the grandparent. Now, when we were discussing AVL trees, we talked about nodes that are bad or out of adjustment with different subtree heights. For instance, the 10 node would be a violation of the AVL condition because it's 2 on the left and 0 on the right. However, with red-black trees, we need to bear in mind the concept of child, parent, and grandparent. So the child always causes the problem. It's the child node that causes the problem. That is, without the child, there's no problem. We have the 10 black and an 8 red. No issues. This satisfies the red-black tree conditions. However, when we put the child in here, we now have a red violation. So the child has caused the problem. The child has caused a red violation. Now then, where is the ant? Well, I think as all of you know, an ant is the sibling of the parent. That is, if you have an ant, that is your parent's sister. So if there were an ant, it would be here. There isn't one though, and since it's a null, it's black. So this is the black ant. This is the black ant condition. For these, you must rotate. A black ant is a rotate, either a single or double. And thankfully, the rotation rules for red-black trees follow as they do for AVL, which means you look at the path you followed doing the insertion. It's a straight line. Therefore, you will have to rotate this, and you will have 8, 5, and 10. This is a rotation because you have a black ant. It's actually a non-existent ant. If there were an ant, it would be right at the 10. So either black because the color of it is black, or because it's not there, a rotation is required. So now, once we have the rotation, we have to recolor these 3 nodes. The root must be black. This is red. And this is red after a rotation. Now the other condition is a color flip. So this is the red ant condition. So we will insert here a 1, and it's red. This causes a red violation. Again, this is the child. The 5 is the parent. The 8 is the grandparent. And the 10 is the ant. This is the sister of the parent. These are siblings. The child is the node that caused the problem. The child caused a red violation. So we look at the ant, and there can only be one because you can only have 2 nodes, our left and right child, for the grandparent. Therefore, the parent exists. If the ant exists, there's only one, and it's unambiguous. And it is red. We have a red ant, therefore we have a color flip. When we do a color flip, we just recolor the nodes without rotating anything. So the general pattern here with the color flip is you have black, red, red. This is the red ant. And this becomes red, black, and black. So you just change the colors of these 3 nodes. Notice too that you maintain the same number of blacks along each path. Here there's a black one black going this way, one black going this way, and here the same thing, one black going this way, one black going this way, but they're down here. So you now have two blacks, but the same number along each path because there are two paths now. So this recoloring step is a way to avoid doing a rotation. So we do the color flip, and let's write our tree over here with the changed colors. There are our 4 nodes. So now we do a color flip. So this is our pattern. We have red, black, black. We have changed the color of each of the 3 nodes. We've toggled them. This was black, it's now red. This was red, it's now black. This was red, it's now black. So we toggle the 3 colors. This, of course, was red and it stays red. So we have done a color flip. Now in this particular case, the 8 is the root node and it cannot be red. Therefore it turns back to black. So these are the 2 scenarios. Again, if you have a black ant, it's there and it's black, or it's not there and is null, that's the black ant condition. In the one we looked at here, the ant is missing, therefore nodes are black. You have a black ant, you must rotate. And you end up with this. The other case is the color flip. The color flip occurs when you have a red ant. The 1 is the child that caused the problem. The parent is the 5. It's also red. The 8 is the grandparent. It's black. There is a red ant. Notice that with red-black trees, it is always the grandparent that fixes things up. That is, we rotated the grandparent here. We initiated the color flip on the grandparent here. This is a case where you have to trace the child, parent, and grandparent, and those are the 3 nodes that are involved. And the ant in case there's a color flip. A useful way to help remember this is to think of families that you may know. The scenario goes like this. The kid gets in trouble. Dad is useless. Grandpa has to come along and clean up the mess. That's an easy way to remember the situation. It's Grandpa's responsibility to clean up the mess. So Grandpa either rotates or does a color flip to clean up the mess and restore the red-black tree to a legal condition. So, walking through these one last time, every node is either red or black. The root node is always black. New insertions, except for the root, are always red. Every path from root to leaf, and recall that a leaf node is one that has no children. Every path from root to leaf must have the same number of black nodes, but it may have an unlimited number of red nodes. No path may have 2 reds in a row, but you may have an unlimited number of blacks in a row. Finally, null references are considered black. So here's an example of a red-black tree. There are 3 leaf nodes, the 5, the 60, and the 95. Every path from the 50, which is the root node, to a leaf node must have the same number of blacks. There are 2 this way, 2 this way, and 2 this way. So when a new node is inserted, it may cause a violation of the red-black tree properties, and the properties that will be violated is the 2 reds in a row. That's what will cause this to happen. In this case, you must adjust the tree in some fashion to bring it back into conformity, and there are 2 ways to do that. Color flip in the case of a red ant, rotation in the case of a black ant. So here's a simple example. The 55 is inserted into the red-black tree. It causes a red violation because we now have 2 reds in a row. The ant is red, so this is the child that caused the problem. This is the parent that's useless. It has no part in fixing things up. It comes along for the ride. And the grandparent, the 90, that has to initiate the fix-up step. So the 90 initiates a color flip. We're going to toggle the colors of the 90, the 60, and the 95. Here we have labeled the nodes that are involved. The 55 is the node that caused the problem. 60 is the parent. 90 is the grandparent. And 95 is the red ant. Since the ant is red, we do a color flip. We toggle the colors of the 90, 60, and the 95. So these are the three nodes that we toggle the colors. The child does not change color. It remains red. And here's the tree after the color flip. The grandparent changes from black to red. The parent changes from red to black. The ant changes from red to black. Now we don't have two in a row. We have actually introduced a red node higher up in the tree. And now the condition is satisfied, and this is a valid red-black tree. Notice again that this is not a valid AVL tree. The 30 would cause this to fail to satisfy the AVL condition because you have 2 on the left and 0 on the right. However, it is a valid red-black tree. So I want to try and demonstrate the rotation situation. So now we're working on the other side of the tree, and we insert a 1 and we have a red violation. We have 2 reds in a row. So we have the child, the parent, the grandparent. The node that caused the problem, the 1, the parent, the 5, 10, the grandparent. Notice that there is no ant. If there were an ant, it would be right here. There isn't one. It's null. We must rotate. So we perform the rotation here and then recolor these nodes. So we have black, red, red after a rotation. And now again we have the same number of black nodes along each path. And the red-black tree condition is now restored. So I want to call your attention to the patterns to look for, to be aware of. After a rotation, the 3 nodes involved in the rotation have this pattern. Black at the top, then red, red. After a color flip, you have red, black, black. Note too that with AVL trees, once you find a node that violates the AVL tree condition and has to be rotated, either a single or a double, once you do one fix-up step, then the tree is restored to the AVL condition. But you're never going to have more than one fix-up step. However, that is not the case with red-black trees. With red-black trees, when you do a color flip like this, it is possible that you will introduce a red violation further up in the tree, and then you will have to deal with that. So it is possible that you may have more than one fix-up step with a red-black tree. Nevertheless, the overall overhead is less than AVL. So I want to do some examples now. So I'm going to insert some nodes into a red-black tree, and we will see how this works. Let's start with a 45. The root node must be black. Now I'm going to insert a 13. New insertions are red. We don't have a red violation, and so this tree is fine. Now I insert a 6. And of course, new insertions are red. I now have a red violation. I have 2 reds in a row. So this is the child, the parent, the grandparent. This is the ant, which is not there. It's null. Because nulls are black, we have a black ant. We must rotate. So we rotate, and we have 13, 6, and 45. And then we recolor black, red, red. This is always the pattern of the 3 nodes involved in a rotation after the rotate. I find it easier to go ahead and do the 3 nodes and attach the colors right away. That way you don't lose track of them. All right, now let's insert an 85. And new insertions are, of course, red. We now have a red violation. The 45 and the 85 are both red, but we have a red ant. Therefore, we need to do a color flip. So we're going to toggle the color of the ant, the parent, and the grandparent. The child is untouched. So recoloring, we have the pattern red, black, and black. But because the 13 is the root node, it cannot be red, it cannot stay red. So we're going to go ahead and switch this back to black. So again, we have the same number of blacks down every path. There are only 2 paths. All right, now I want to insert a 75. So I'm going to insert a 75 here. It's red, it's a new insertion, and we have a red violation. Since we have a red violation, we now have to look at the ant and see whether it's red or black. This is the child, the 85 is the parent, the 45 is the grandparent. If there were an ant, it would be here, but there isn't one, it's black, therefore we have rotation. With rotation, we must rotate the grandparent. This is the path that we followed along the insertion. It is not a straight line. So the same rules apply that applied in the case of AVL trees. We need to rotate the 45 to the lighter side. It needs to be rotated left, which means we must rotate the 85 to the right first. So we do this, and we have 13, 6, 45, 75, 85. That's the first of the 2 rotations that are required. We've rotated the 85 to the right, and now we need to rotate the 45 to the left, and that leaves us with 13, 6, 75, the 45, and the 85. Now let's color these. The 13 was black before and it still is. It hasn't been touched. The 6 is black. It wasn't involved in any of this. It has not changed colors. The 3 nodes involved in the rotation are here, and after a rotate we have black, red, red. Doesn't matter what they were before. After a rotate we have black at the root of that subtree, and then the left and right children are always red. So let me rewrite this on the other side so that we can continue this discussion. So okay, I have just moved our tree up to the side here so we can continue our discussion. And now I want to insert an 80. And it's red. So we have a red violation. The 80 and the 85 are both red. This is not allowed. We must go to the grandparent and identify the ant, child, 85 the parent, 75 the grandparent, 45 the ant. The ant is red. Therefore, we must do a color flip. That means the grandparent, ant, and parent colors get toggled. We're going to have the pattern red here, black, black on the 45 and 85. So I toggle the colors here. And now we have red, black, and black. So again, this tree would not satisfy the AVL condition, but it satisfies the red-black tree condition. We have the same number of black nodes in every path from root to leaf. The leaf nodes are 6, 45, and 80. Along this path, the 13, 6, 2 blacks. 13, 75, 45, 2 blacks. 13, 75, 85, 80, 2 blacks. The number of reds is unimportant. Now I want to insert an 83. And of course, new insertions are red, and we have a red violation. Good. So now we're going to have to handle the red violation by rotation, because this is the child, the 83. The 80 is the parent. The 85 is the grandparent. There is no aunt, therefore it's black. A rotation is required. So let's do that. We have 13, 6, 75, 45. To simplify, I'm doing this all in one step. Notice that here we need to rotate the 85 to the light side. The right subtree is empty. 85 needs to go this way, therefore the 80 has to go this way, which will pull the 83 up here. That will be the new top or the new root. 83, 80, 85. So I've just done this in one step here to simplify. Now recolor these three nodes that we have just rotated. The 83 was red, but it is now black. The 80 is red. The 85 is red. The 75 is red. It did not change. Black, black, black. Again, we have the same number of black nodes from root to leaf. This tree looks like it's extremely unbalanced, and in fact it is. But we shall see what happens when we continue to add nodes. So now I want to add a 90. Of course, new insertions are red. And so we examine the aunt. This 90 is the child, 85 is the parent, 83 is the grandparent, 80 is the aunt. We have a red aunt. Therefore, we do a color flip. That is, we need to toggle the parent, the grandparent, and the aunt. These three nodes, we flip or toggle their colors. So we're going to have red, black, black. All right, that step is done, but notice that the 83 has introduced a red violation higher up in the tree. So when you're working with AVL trees, a single fix-up step, a single or double rotation, will always restore the tree back to a valid AVL condition, but that's not the case with red-black trees. We did one fix-up step, we did this color flip, but doing the color flip introduced a red violation higher up in the tree. So now we have another red violation that we must handle. So now we have two fix-up steps that will be required. So this is the child. This is the parent. This is the grandparent. I label these because it's important to keep track of the role of each of these nodes in this process. This is the aunt. As is the case with AVL trees, it won't do to simply rotate or flip some node to get the desired result. It's got to be unambiguous which one gets flipped, which ones get rotated. Therefore, remember the rule, it's always the grandparent that initiates the fix-up. So the ant is black. We have the child, the 83. This is what caused the violation. The child always causes the violation. We have 2 reds in a row. The parent did nothing. It was the child that came in and flipped colors, and now you have 2 reds in a row. So the child, the parent, the grandparent, and we have a black ant, which means we must rotate. Now our insertion path was this way. Therefore, the 3 nodes that need to be rotated are these, and we have a straight line. Now, granted, this wasn't the node we just inserted. That's not what we did. We inserted the 90. However, this node caused the red violation. Therefore, we must rotate its grandparent, the 13. So we do that. And I find it easiest to write the 3 nodes that are involved in the rotation first. The 75 is going to be the new root. The 13 will be pulled down. Therefore, the 13 is pulled down. And here we have the 83. So these are the 3 nodes that are involved in the rotation. 13, 75, 83 become 13, 75, 83. Now we have black, red, and red after a rotation. Now we have the 6 that did not move. It was the left child of the 13, and it still is. It's black. Notice that the 45 has to change sides. The 45 was the left child of the 75, but it can't be any more. Therefore, it switches sides. And again, what we're looking at is this is what is in between the 13 and the 75. That 45 can go on either side, so it goes here. That node was black. It still is. It merely switched sides. Now over here we have 83, we have 80, 85, and 90. Again, these nodes retain the colors they had before. The 85 is black, the 90 is red. So now again we're done, and we have a far more balanced tree at this point. So we have precisely 2 black nodes down every path from root to leaf. Well, now we have 1, 2, 3, 4 leaf nodes, but again, the 90 back to the 75, there are 2 blacks. The 80 back to the 75, there are 2 blacks. The 45 back to the 75, there are 2 blacks. The 6 back to the 75, there are 2 blacks. So again, I'm going to go ahead and copy this tree up to the corner and clear our space so we can continue this demo. Okay, we have relocated our tree up in the corner to get more scratch space. Now let's insert 150. And of course it's red. This requires a simple rotation. We have the child 150, the parent the 90, the grandparent the 85. The ant is not there, it's black. Therefore, we must rotate. And I'm going to have to do this right in place rather than rewriting the entire tree just for simplicity. So we have 90, 85, and 150. Now after a rotate, we have black, red, red. We always have this after a rotate. And the tree's condition is restored. We have the same number of black nodes. All right, now I'm going to insert 200. And it's red. So now again I have a red violation. 200 is the child, 150 is the parent, 90 is the grandchild, 85 is the ant. I have a red ant, therefore I do a color flip. So I toggle the grandparent, the parent, and the ant. These nodes, I'm going to toggle the colors. The black I'm going to make red, the red I'm going to make black. So we have red, black, black. We have red, black, and black. But notice that this has caused a violation higher up in the tree. Now the 90 is the child node, and this has caused a red violation because the 83 is also red. So the child, of course, is useless to fix the problem. It falls on Grandpa, the 75. Therefore, the three nodes that are involved here, this is red. We have a red ant. Child, parent is the 83. Grandparent is the 75. The 13 is the ant, and it's red. Therefore, we're going to toggle these colors. So we do this, and we now have red, black, black. The root node cannot be red, so we recolor this back to black. So now again we have the same number of black nodes down every path. We have 3 blacks each direction from root to leaf. 6 is a leaf node. The 6 back to the 75 we have 3 blacks. The 45 back to the 75 we have 3 blacks. The 80 back to the 75 we have 3 blacks. The 85 back to the 75 we have 3 blacks. The 200 back to the 75 we have 3 blacks. All right. Now let's add a 210. As you can see, of course, the tree we have at this point in no way would satisfy the AVL condition. That would be impossible. However, it does satisfy the red-black tree condition. So now again, we have a red violation. We have 2 reds in a row. What color is the ant? This is the child, the 210. The 200 is the parent. The 150 is the grandparent. If there were an ant, it would be here. There isn't one, therefore we have a black ant condition, and we must rotate. So I'm going to go ahead and do this in place to save space and time. We have 150, 200, 210. We rotate the 150 to the left. So we have 200, 150, and 210. So having done the rotation, now we recolor, and this is black, red, red. This is always the pattern after a rotation. So again, we have restored this to a valid red-black tree condition. So let's insert a 250. And of course it will be red. So now we have 2 reds in a row. We have a violation. So this 250 is the child, 210 is the parent, 200 the grandparent, 150 is the ant, and it's red, so we have a color flip. The nodes involved in the color flip are these: the parent, the ant, and the grandparent. The colors get toggled. We have red, black, black. Notice now that we have introduced a red violation higher up in the tree. Now, it's important that you maintain your or keep track of the role of each of the nodes in this process, because you might be tempted to rotate or move the wrong node. But it has to be unambiguous. This is the child that caused the problem. This is the parent. This is the grandparent. Therefore, the grandparent must do the fix-up step. This 80 is the aunt. It's black, therefore we must rotate. We rotate to the light side. We need to rotate the 83 to the left. Now we need to look at the path here. It is a straight line. Therefore, a simple left rotation of the 83 will restore the tree to its proper state. So rewriting our tree, then we have 75, 13, 6, 45. Then over here we have the rotation. So I want to write those three nodes before I do anything else on this subtree. We're going to drop the 83 down and pull the 90 up. So these are the three nodes here that we're working on right now. So we have 90, 83, 200. Now we have 80 here. Let's color these nodes. After a rotate, we have black, red, and red. The other nodes retain the colors that they had before. Okay, we have the 90. The 85 has to switch sides. It goes here. Off the 200, we have 150, 210, and 250. Recoloring, we have black. The 13 is black. It did not change. Black. The 45 is black. The 80 was black before, and it still is. The 85 was black before, and it keeps that color. The 150, black. The 210, black. And then the 150 is red. So again, we have three blacks for every path from root to leaf. The longest path here, the 250 back to the 75, we have 1, 2, 3 blacks. So this is a valid red-black tree. As you can see, you can have trees that are, by AVL standards, way out of adjustment. However, when the step that's been delayed, that is, a more unbalanced tree appears to be possible with these, when you do fix it up, it has a more dramatic effect and it lowers the height of the tree. So this concludes our discussion of red-black trees. Again, we have looked at AVL trees and red-black trees. AVL trees were first described about 60 years ago. We've only looked at insertions. The deletion part of this is more complicated and not really necessary for this course. What we want you to understand is the mechanisms by which you can readjust a tree and avoid that worst case behavior of standard binary search trees. AVL trees are seldom used because of the extra storage requirements in the overhead. Red-black trees are very commonly used because they really are the most efficient way to handle this balanced condition. AVL trees are on average about 1.44 log in height, whereas red-black trees can be as bad as 2 log in for the height. This, however, is still log n. 2 log n is not a serious concern. Finally, one thing I want to mention, sometimes students look at the color flip and think that red-black trees are more efficient because color flips are easier to do. I suppose many students have an idea of nodes being rotated around inside memory, and that seems to imply moving things. However, understand that whether you're doing rotations or you're doing color flips, what you have are nothing more than simple assignment statements. Therefore, a color flip that involves 3 assignment statements is no better or no worse than a rotation that has 3 assignment statements. Therefore, the idea that color flips are more efficient than rotation is simply not true. Red-black trees are chosen over AVL trees because they require less memory, and the overhead of recalculating the height of the subtrees makes them slower with empirical times, that is, wall clock time. So this then concludes our lecture.